In this chapter, chapter 2, we're going to talk about atoms, molecules, and ions. We're going to start off with this video on atomic theory. So let's get started. So to discuss atomic theory, we have to understand where the atomic theory came from. Originally, the atomic theory was proposed by a Greek philosopher named Democritus. And his argument went like this. If you tear a piece of paper in half, and then you tear the half in half, and you tear the quarter in half, and you tear the eighth in half, and so on and so forth, eventually you'll end up with a piece that is the tiniest indivisible portion, and he called that atomos. Come along a few centuries later, and we have a guy named John Dalton, an Englishman. And what he did was he came up with a modern view of what the atom is. So these are the postulates to Dalton's atomic theory, that elements are made of indivisible particles, the atom, and that all atoms of an element are the same. In other words, an atom of hydrogen is an atom of hydrogen. But different atoms are different, so an atom of hydrogen is not the same as an atom of oxygen, which is kind of an important distinction. And he also said that different elements will combine to form compounds. Now, the way they combine is that it's always going to occur in the same ratio by mass. In other words, if we have water, regardless of the source, whether it came from the Himalayas or it came from Rockford Municipal, it is always going to be the same by mass amount of hydrogen to oxygen. That's 1 gram of hydrogen for every 8 grams of oxygen. And finally, we have that atoms are neither created nor destroyed in a chemical reaction, that we just simply rearrange the atoms. And this is known as the law of conservation of matter, which is a very important law, is that you cannot create or destroy matter. Now, this atomic theory, Dalton's atomic theory, didn't hold up for very long, because there were some great discoveries in physics that happened in the late 1800s and early 1900s. These experiments and these people are crucial to our modern understanding of the atom. First, we have J.J. Thomson. His work led directly to the discovery of the electron. And then Robert Millikan, who his work came later than Thomson, but allowed us to determine the mass and charge on the electron. Henri Becquerel, who taught us about radioactivity. Rutherford, who gave us a better modern understanding of the atom and how all the different pieces were put together. And then finally James Chadwick, who taught us about the neutron. Now, the really, really important ones that you're going to have to know is you should know the J.J. Thomson experiment, the Millikan experiment, and especially the Rutherford experiment. I will go into great detail on the Rutherford experiment, so it's a very important experiment that has changed the way we have viewed the atom. So let's start off with J.J. Thomson's experiment. Now, J.J. took what's known as a Crookes tube, named after the guy who invented Crookes, and what he was doing was he was studying the transmission of electricity through gases. And what he found was that he could pass electricity through no gas at all. And he ended up with a beam of what he called cathode rays. And as he did this experiment, he changed the magnetic field and the electric field around the tube, and he could deflect the rays. Now, what this led to was that these cathode rays, or these corpuscles of electricity, he also called them, were what we call now electrons. And from this, he actually could calculate the charge to mass ratio of the electron. And that is 1.76 times 10 to the 8th coulombs per gram. Now, what this really means is this charge to mass ratio kind of gives us an idea that the electron has got a pretty big charge for a very small mass, because that is a really big ratio. You can still see the work on cathode rays if you have an old tube-style TV. If you place a magnet on the front of a tube-style TV, it will actually change the colors, because the cathode ray tube, or the CRT displays of the old televisions, actually shot electrons at a phosphorescent screen. This says fluorescent, but that's not true. It was a phosphorescent screen. And that's what gave us the different colors. So if you put that magnet up, you change the deflection of those beams and change the colors. The Millikan oil drop experiment, conducted by Robert Millikan in the 1920s, about 20 years after the discovery of the electron, is where we finally get to be able to measure the charge on the electron. And so he measured the charge on the electron to be 1.6 times 10 to the minus 19th coulombs. And knowing the charge to mass ratio, he can calculate the mass on the electron, or about 9 times 10 to the minus 28 grams. So a very, very, very small particle. Now, the way he did this was he took an atomizer, which is simply just a fine spray of oil droplets into an evacuated chamber, which had a hole in it. And it had these negative and positively charged plates on here, and an X-ray beam, which would hit the oil droplets and charge those droplets. It would knock the electrons off. And by varying the charge between these two plates, he could actually get the oil droplets to fall at a consistent rate, or even stop midair, or even move up. And knowing these different charge on here, through many hours of experimentation, he was able to measure that electron charge. Now, to understand the next series of experiments, we have to understand what radioactivity is. And I start off by talking about pitchblende, which was a rock that was always warm. Didn't matter what the temperature was out, that this rock would feel warm. And it was a big hit in Victorian era England. But the thing is it's a radioactive rock. It's a radioactive ore of uranium. And a gentleman named Henri Becquerel had worked with some pitchblende, and I'll save you the big boring story, but he placed the pitchblende on photographic plates, and it fogs up the photographic plates. And then what that fogging of the photographic plates was, a guy named William Röntgen called them X-rays, which makes sense because we know what we can use X-rays for. That is to image bones. Well, it was originally shooting the X-rays at a photographic plate. That's where you get your photos of your bones. Now, radioactivity as a phenomenon was characterized by Ernest Rutherford. And you can see from these experiments here that there are three basic radioactive particles. There's the alpha particle, the beta particle, and the gamma particle. Now, how he characterized these is he had a radioactive source, and he passed it through a charged field. And the alpha particles are deflected toward the negative pole, which means that the alpha particles must be positively charged. The beta particles are deflected toward the positive side, which means that a beta particle must be negatively charged. And then our gamma rays go straight through. They're not affected by the field, which means they have no charge. We know now that an alpha particle is a helium nucleus stripped of its electrons, and a beta particle is a high-energy electron. And the gamma is actually a high-energy photon, or a source of electromagnetic radiation. So now we have some basic information we need to understand the model of the atom put forth at the time. This was known as the plum pudding model. And if you've never had plum pudding, I can make a much better analogy if I talk about chocolate chip cookie dough. The model put forth by Thomson was that the atom was this positively charged goo that held these negative electrons within them, much like the chocolate chip cookie dough and then the chocolate chips. So in order to test this model of the atom, Ernest Rutherford came up with a very ingenious experiment. Now, what Rutherford did is he took a thin sheet of gold foil and he shot an alpha particle stream at that gold foil. And he had a detecting screen surrounding the foil. And what happened is those alpha particles would go toward the gold surface, and most of the time they'd go right through. As you can see these arrows, they'd just shoot right through the gold foil. But every once in a while, you'd see some deflection to the sides, or even an outright bounce back. Now, this experiment is super duper important because of what this led to. So make sure you know the setup of the gold foil experiment and the consequences of the gold foil experiment. These consequences are that atoms have a dense inner core that is positively charged. In other words, we now have the nuclear atom. The nucleus is where all the mass of the atom is contained, and that the electrons surround the nucleus that are nearly massless. Okay? Now, the interesting thing about this is this led to the discovery of the proton, the positively charged subatomic particle. And that is contained within the nucleus. That's that core of positive charge. But probably the scariest thing is that what this really means is since most of the alpha particles went right through undeflected, that the volume of the atom is mostly empty space. And to illustrate that, if I blow the nucleus up to the size of a little normal green pea, the nearest electron would be orbiting a mile away. And the distance between that pea and the nearest electron, there's nothing. Nothingness. It's just incredibly mind-blowing to think that there's nothing there. It is completely nothing. That's just freaky. Now, today we also know that there is the neutron. That brings out our third subatomic particle. So we've got the electron, negatively charged, the proton, positively charged, and the neutron, which has no charge. It has the same mass as the proton, but no charge. This was discovered through nuclear reactions in 1932. But it was theorized back by Chadwick and Rutherford because they couldn't wrap their minds around how we had all these positive charges hanging out in a dense core. And the reason it was hard to discover was because it has no charge. One of my favorite jokes is a neutron walks into a bar and orders a shot and asks the bartender how much, and the bartender says, "For you, no charge." But the neutron has a very important role. Since it has the mass of the proton, that means that it helps to make up the mass of the atom. And then its other role is to mediate the interactions of the protons. Because when you have two positive charges coming together, they should repel each other. But yet in the nucleus, you've got lots of positive charges coming together and staying together in a stable arrangement. The reason they're stable is because of the neutron. So let's run down our subatomic particles. First off, we have the proton, which is given the symbol P with a positive exponent. It has a positive charge and has a mass of 1.67 times 10 to the minus 24 grams. The number of protons within an atom is the atomic number, and we symbolize that as Z. The atomic number, or the number of protons, gives the element its identity. So, for example, hydrogen with an atomic number of 1 has 1 proton. Lithium with an atomic number of 3 has 3 protons. Uranium with an atomic number of 92 has 92 protons. Now, the electrons, which are symbolized E with a negative exponent, have a negative charge and are quite small compared to the proton. They're effectively massless compared to the size of that proton, at 9.1 times 10 to the minus 28 grams. For a neutral atom, the number of electrons must equal the atomic number or the number of protons. So, if I've got hydrogen with 1 proton, to be a neutral atom, it has to have 1 electron. If I've got lithium with 3 protons, it must have 3 electrons. Uranium with 92 protons, you got it, 92 electrons. Now, the neutrons, we give the symbol N, or sometimes N with a 0 subscript, and these have no charge, and you can see the mass is about the same as that of the proton. We symbolize the mass number as A, which is the total number of protons and the total number of neutrons. This is where the mass comes from in the atom. So if we take a look at hydrogen, which has got a mass of about 1, then that means it's just got a proton and no neutrons. If we take a look at helium, which has got a mass number of 4, that means that it's got 2 protons and 2 neutrons. Now, the number of neutrons in an atom is variable. We call these isotopes. Now, we symbolize isotopes in the following manner. We take X, where that is the element symbol. We put the mass number as a superscript on the left-hand side and the atomic number as a subscript on the right-hand side. So here we have 3 isotopes of hydrogen. We have hydrogen with a mass number of 1 and an atomic number of 1. Hydrogen with a mass number of 2, atomic number of 1. Hydrogen with a mass number of 3 and an atomic number of 1. And I apologize for the fact that they've shifted. But here is the interesting thing. They're all hydrogen, so the atomic number has to be the same for each case. And you can see how many protons we have. That's just 1. How many protons? 1. How many protons? 1. But the number of neutrons is variable. For this, hydrogen with a mass number of 1, the mass minus the number of protons is the number of neutrons. So 1 minus 1, 0 neutrons. Mass number of 2 minus 1, that means we've got 1 neutron. And 3 minus 1, we've got 2 neutrons. We can also write this as the element name followed by the mass number, such as carbon-14 or carbon-12. Now, the chemical properties of isotopes are identical for our purposes. In other words, hydrogen doesn't matter whether it's this form of hydrogen, this isotope of hydrogen, this isotope, or this isotope. The properties we're going to look at are going to be identical. So this wraps up our quick introduction to modern atomic theory.